visible to all of you?
Yes, sir.
Fine. Actually, I already told you about some special lectures. Okay, so for our course, we arranged two special lectures from company side. Okay, so it is actually next week Tuesday. Okay, not today. So it is next week. So in today's session, we will continue the nonlinear data structure, the tree concept. In our last session, we started discussing about nonlinear data structure. What is a nonlinear data structure? And under nonlinear data structure, we are going to discuss about trees and graphs concept. So first we started with the trees. So what is a tree and what are the important terminologies of a tree? So important terminology means what is the root of a tree, what is intermediate nodes, child nodes, ancestors, dependents, what is a path, what is the level of a node, what is the height of a tree. Okay, so all these things we discussed in our last class, okay, last session. Okay, so today's session we will discuss in detail about binary trees. So last session we had given introduction to binary tree. So binary tree means each node can have maximum two subtrees, two childs. Okay, so it can have zero child or one child or two child, zero subtree or one subtree or two subtrees as given in this picture. Okay, so this is called as a binary tree. In binary tree, each node can have maximum of two subtrees or two child nodes. Okay, so this is what binary tree. Okay, so example, so these are by example binary trees. The first one, A is a null tree. Okay, if there is no node in a tree, it is called as a null tree. Okay, and no a tree with only one single node, then two nodes. Okay, only left child is there. Then that example D is again two nodes, only one right child is there. Then example E, a node, root node with two child nodes, B and C, one left child and one right child. Okay, left side node, right side node. And F, okay, so it is having three levels. Okay, so height of three. Okay, so A, B, C, D, E. Okay, and then G is also binary tree. Okay, and H also a binary tree. Okay, these are different examples of binary trees. All these are binary trees. Okay, now what are the important properties of a binary tree? Okay, so some of the binary tree properties we are going to discuss. What are the properties means? Okay, so first one is it is related to height of a binary tree. Suppose if n value is given to you, here what is the n value means? The number of nodes in a binary tree. Suppose n value is given to you, then for that n value, what is the maximum height of a binary tree we can create, and what is the minimum height of a binary tree we need to insert all the n nodes. Okay, so this is what maximum height and minimum height. Okay, so maximum height of a binary tree for the given n nodes is n, h max equal to n. Okay, so just 1 minute. Okay, so this, there is no meaning for this circle. I'll erase this before uploading the PPT. Okay, so h max equal to n. Suppose if n value is given to you as a three nodes. Okay, if a binary tree can contain three nodes means what are all the possible tree structures you can create? Okay, it will be like this. So if three nodes is given to you, then okay, so this is one type of structure, and this is another type of structure, and this is another type of structure, and this is another type of structure. Okay, and this is another type of structure. So these are all different possibilities of binary tree we can create using tree nodes. In this, what is the height of the first tree? So this is first tree. So what is the height of the first tree? 2. What is the height of the 2, 3, 4 and 5?
3, sir.
3. See, if the number of nodes given to you is 3 means the maximum height that we can create. Okay, maximum, yeah, the binary tree that we can create with the maximum height is a 3. Okay, so 3 maximum height is a 3. That is what here they are mentioning. Okay, h max equal to n. If n nodes is given to you, you can create a binary tree with max height of a n. Okay, it is not possible to create more than that height. So that is what the first property, h max. The second property is minimum height. Okay, suppose if a n nodes is given to you, okay, then what is the minimum height we need for the binary tree to accommodate all the n nodes? Okay, for that the formula is log n base 2 plus 1. Okay, so it is this symbol. Okay, so okay, so this symbol is flooring. Okay, we need to round off to the previous integer, flooring option. Okay, so this symbol. Okay, so we need to calculate the log n base 2 and it must be rounded off to the previous integer and we need to add with 1. So this is h min. Okay, suppose if the same, instead of 4, okay, let us take instead of 3, let us take 5, n value as a 5. Okay, for n value 5, what is the maximum and minimum node that we can create? Okay, so minimum tree we can create, minimum binary tree. Okay, so let us check it. Okay, so suppose if a number of nodes given to us is a 5, okay, then using 5 nodes, binary tree with minimum height we need to create. Okay, so first node we created. Okay, then for it left node and right node. Now what is the height means 2. Okay, but only 3 nodes we accommodated. So next is this one. Okay, 4 and 5. Okay, so this is the binary tree with minimum height we can create using 5 nodes. Okay, 1 2 3 4 5. Okay, and what is the formula given here? Okay, log n base 2. What is the log 5 base 2 value? What is the log 5 base 2 value?
2 point something.
2 point something. So 2 point something means if you are rounding it, rounding up to the previous integer, okay, it is a 2. Okay, so 2 plus 1 is how much? 3. Okay, see here. What is the height of this tree? 1 2 3. So yeah, binary tree with the minimum height 3 we need to accommodate 5 nodes. The same for 6 and 7 also. Suppose if 8 is given, okay, number of nodes is 8. To accommodate 8 nodes, a binary tree with minimum height how much required? It means that what is the value of log 8 base 2?
3, sir.
3. 3 plus 1 is how much? 4. 3 plus 1 is 4. There is a formula here. See here, log 8 base 2, it is 3 plus 1 is 4. Okay, suppose if 8 nodes is given to you, 1 2 3 4 5 and 6, then 7 and then 8. Okay, so 8 nodes we inserted in the binary tree, and what is the height? 1 2 3 and 4. 4 is the height of this binary tree. So we need a binary tree with minimum height of 4 to accommodate 8 nodes. Okay, so this is the second property, h min. It is both are called as both are related to height property. Okay, maximum height to accommodate n nodes and minimum height to accommodate n nodes. Okay, so the next property. Okay, suppose if number of nodes is given, minimum nodes. Okay, so if height is given, just opposite to the previous. In the previous property, number of nodes is given and we calculated height. Here height is given. If in that height, what is the minimum number of nodes we can accommodate and what is the maximum number of nodes we can accommodate? That is what we are going to calculate. So minimum nodes, we can turn the calculation around and determine the minimum number of nodes in a tree of a specified height. Suppose height is given. If a height is given as a 3, okay, then what is the minimum number of nodes we can store? Means it is equal to height. Okay, suppose if 3 is given as a height, okay, 3 is given as a height means then minimum we can insert 3 nodes. Okay, minimum we can insert 3 nodes. Okay, this is for height is given as a 3. Okay, height is given as a 3, and minimum we can insert 3 nodes. Okay, minimum we can insert 3 nodes. So this is what, if the height is given, the number of minimum nodes we can insert in the binary tree, and maximum nodes. Okay, suppose if h is given, okay, and how many number of maximum nodes we can insert means it is a 2 power h minus 1. Okay, it is 2 power h minus 1. Suppose the same height is given as a 3 means 2 power 3 is how much? 8. 8 minus 1 is how much? 7. Okay, see here in this same node. Okay, so we can insert okay, so this is a 3, h is given as a 3, and the maximum n we can store is a, okay, maximum n we can store is a 7. Okay, 7. It is 2 power h minus 1. Okay, that is 2 power 3 minus 1. So totally 7 nodes we inserted in the binary tree with the height 3. So this is what, this is how we can calculate n min and n max. In the previous property we calculated h max and h min. Here we are calculating n min and n max. If height is given, then how many nodes we can insert in that binary tree, minimum and maximum number of nodes. Okay, so the next property is balance. Okay, this is very, very important because based on this the next tree we are going to discuss, that is AVL tree. Okay, so AVL tree is balanced binary tree. It is called as a balanced binary tree. Okay, so that how to implement that is based on this balance. What is this balancing means? The distance of a node from the root. Okay, it determines how efficiently it can be located. Okay, if you are taking a binary tree, okay, so from in a binary tree, how to reach this node? Okay, to reach this, suppose let us, if you are having a numbers for this mean, okay, numbers means 1, 2, 3, 4, 5, 6, 7, 8. Okay, suppose if you wish to reach 8th node, then how many edges we need to pass? 1, 2, and 3. Okay, we can reach the path. Okay, so we can reach the path efficiently after crossing 3 edges. Okay, nodes and edges. Okay, now suppose if you wish to reach 5 means we need to cross only 2 paths. Okay, instead of this, if the same 8 nodes are arranged like this, 1, 2, 3, 4, 5, 6, 7, and then one more is 8. So 1, 2, 3, 4, 5, 6, 7. So this is also a binary tree. Okay, so for this node also only one node is a child node, and for this also one subtree, and for this 2 subtrees, and for this 2 subtrees, and for this only one subtree. Okay, now this is the 8th node. Okay, this is the 8th node. If you wish to reach 8th node means how many paths we need to traverse? 1, 2, 3, 4, and 5. Okay, here only 3 paths, means 3 edges we need to cross, but here we need to cross 8 edges. So to reach 8, okay, so it requires more traversals. Okay, so if a binary tree is balanced properly, balanced means if for the given height all the nodes are accommodated properly, okay, then to reach a node we need minimum number of paths. Okay, if it is not balanced properly, okay, for the given height the number of nodes filled, okay, if it is not properly filled, then if it is not balanced, then we need more paths to access a node. Okay, so this is one of the advantage of arranging the nodes properly for the given height. Okay, so this can be achieved by balancing the nodes. Okay, so the children of any node in a tree can be accessed by following only one branch path. Okay, only one branch path, the one that leads to the desired node. Okay, so any node can be accessed by traversing the branch path. Okay, it is unique for each and every node in the tree. Okay, the node at level 1, which are children of the root node, can be accessed by following only one branch. Okay, see here 2 and 3 are immediate children of 1, so it can be accessed by only one branch. Okay, and similarly the node at level 2 of a tree can all accessed by following 2 branches from the root. Okay, here these are in the level 2, 4, 5, 6, 7, these are in the level 2. So if you wish to access 4 or 5 or 6 or 7, we need to cross only 2 branches. Okay, we need to cross only 2 branches. Okay, and the shorter the tree, it is easier to locate any desired node. Okay, here also we have 8 nodes, and here also we have 8 nodes. What is the height of this tree is 4, and what is the height of this tree is 1, 2, 3, and 4, 5,
Sir.
6. Yes.
6, sir. I was saying.
6, yeah, 6. Okay, so compared to the height, this means this binary tree height is 4, and this binary tree height is 8. Sorry, 6. Okay, so in this, okay, shorter the tree, we can easily access the nodes. That is what here they are mentioning. Okay, shorter the tree, it is easier to locate the nodes in the tree. Okay, this concept leads very important characteristics, that is balancing. Okay, if each node is balanced properly, then it is the tree will be very shorter, and we can easily access all the nodes. Okay, so that is what here they are mentioning. To determine whether a tree is balanced, we need to calculate balance factor. So how to calculate balance factor means B equal to HL minus HR. That is height of the left subtree minus height of the right subtree. Okay, it is what called as a balance factor. Okay, suppose here if you are taking, okay, for 1, what is the left subtree height? Okay, left subtree height is 1, 2, 3. Okay, right subtree height is 1, 2. Okay, and 3 minus 2 is how much? 1. Okay, the balance factor must be either 0 or 1 or minus 1. Okay, it should be for all the nodes in a tree. Then it is called as a balanced tree. Okay, then it is called as a balanced tree. Suppose if you are taking 2, for 2, left side tree height is 1, 2, and right side is 1. So 2 minus 1 is 1. The same way, 3, left side is 1, right side is 1. 1 minus 1 is 0. For 4, left side is 8 and right side is 0. Sorry, left side is 1 and right side is 0. 1 minus 0 is 1. For 5, 6, 7, it is 0. Okay. The same way, if you are taking this example, okay, here, what is the height of the left subtree means 1, 2, 3, 4, and 5. 5 minus right side is 0. 5 minus 0 is how much? 5. Okay. This tree is not balanced. Okay, it is not balanced. It is not balanced. Okay, so this is what balance factor. The balance factor of a binary tree is the difference in the height between its left subtree and right subtree. B equal to HL minus HR. Okay, and the balanced binary tree means the height of its subtree difference. Okay, it should be minus 1 or 0 or 1. Okay, then the tree is a balanced binary tree. Okay, it should be for all the nodes in the binary tree. Then only it's called as a balanced binary tree. And the balanced binary tree is called as a ABL tree. So ABL tree means it is a balanced binary tree. Okay, it is created by scientists Adelson, Velsky, and Landis. Okay, based on their name, this tree is called ABL tree. Okay, ABL tree means it is a balanced binary tree. Okay, now the next definitions: complete binary tree and a nearly complete binary tree. So complete binary tree means for the given height, the maximum number of nodes, okay, it should be filled. Then it is called as a complete binary tree. Okay, if height is 1, there should be 1 node maximum. Okay, so it must be there. If height is 2 means, okay, then 3 nodes must be there. Okay, so how to calculate this maximum nodes for the given height? It is a 2 power h minus 1. Okay, so here height is 2. Okay, height is 2 means, okay, how much? 2 power 2 minus 1. Okay, 2 power 2 is 4 minus 1. So totally 3 nodes must be there. 1, 2, 3. Okay, and here height is 3. Okay, 3 means 2 power 3 minus 1. Okay, 3 minus 1 means 8 minus 1, 7 nodes. Okay, 1, 2, 3, 4, 5, 6, 7. 7 nodes. So this is what called as a complete binary tree. A complete binary tree has the maximum number of entries for the given height, for its height. Okay, so if it is reached and the last level is full means it is called as a complete binary tree. Okay, complete binary tree. Now what is a nearly complete binary tree means? Nearly complete binary tree, okay, all the nodes means the maximum number of nodes for a given height will be filled, and if any nodes are not filled means only it will be in the right child. Okay, so right child will be empty. Then it is called as a nearly complete binary tree. Okay, here if you are taking for A, 2 childs are there. Okay, for B, left child is there but no right child. Okay, it is a nearly complete. Instead, if it is given like B right side, okay, right side D is given and the left side is empty means, okay, it is not nearly complete binary tree. The empty place should be only in the right side of a node. Then it is called as a nearly complete binary tree. Okay, see here A, B, C. Okay, for A, 2 subtrees are there. For B, D and E, 2 subtrees are there. For C, no childs. Okay, it is allowed. Okay, or it can have one left subtree F. Okay, if it is having a right subtree means it is not a valid nearly complete binary tree. Okay, only the empty positions, okay, empty nodes, it should be in the right side of a node. Then it is called as a nearly complete binary tree. Okay, so this is what definition for complete and nearly complete binary trees. Okay, the next is a binary tree traversals. Okay, the traversal is a very important part. In linked list, once we inserted all the nodes, what are the things we implemented means we traversed the linked list in forward direction. Okay, and in the doubly linked list, we performed the traversal in the forward direction and also in the backward direction. Okay, you can use the traversal for displaying the values or any other purpose. Suppose if you want to perform any conditions, okay, for, count all the odd numbers in the list, count all the even numbers in the list. Okay, so if you want to process any value, okay, the values in the node, for that we need to perform the traversal. So the traversal is important. So in linked list, we traversed linearly. Okay, in binary tree, how we need to traversal? Okay, how we need to implement the traversal concept. Here in a binary tree, we have two approaches, the traversal approaches. The first one is called as a depth first traversal, and the second one is called as a breadth first traversal. Okay, so depth first and breadth first. Depth first means first all the child node will be traversed, then root node will be traversed, visited. Okay, it will go to the child node, then it will come to the root node and visit it. So this is depth first. Okay, breadth first means first siblings. Okay, siblings will be visited. Okay, and then it will go to the child node. Okay, root node and all the root nodes. Okay, so level by level it will go. So this is what BFT, breadth first traversal, and DFT, depth first traversal. And under depth first traversal, we have 3 types of traversal, that is called as a pre-order traversal, post-order traversal, and in-order traversal. Okay, depth first traversal, processing proceeds along a path from the root to one child. Okay, so in depth first, from root it will go to the leftmost child, then its root, then its root. Like that, it will traversal will come. Okay, and in breadth first traversal, processing proceeds horizontally from the root to all of its children, then all its children. Okay, like that. Okay. Example for DFT. Okay, as I already told you, in depth first traversal, we have 3 types. Okay, 3 subcategories. That is the pre-order traversal, in-order traversal, and the post-order traversal. Okay, so this is very, very important. See here. Suppose if we have 3 nodes, 1, 2, and 3. Okay, pre, in, and post. What is the meaning of this pre-order, in-order, post-order means? When we are visiting the root node. Okay, so based on that, we can say it is a pre or in or post-order. If you are visiting the root node first, okay, then it is called a pre-order. If you are visiting the root node after visiting left subtree, then root, then right subtree, it is in order. Okay, and the post-order means we will visit the root node at the end. So we will visit the left node first, then right node, then root node. Okay, so this is what called as a post-order traversal. Okay, so here they have given one tree for this. What is the pre-order traversal, in-order traversal, and post-order traversal? We will see. Okay. Now pre-order traversal. Pre-order traversal, here it is given as a N, L, and R. N means root node, then left node, then right node. Okay. N is a root node. Okay. So visiting the root node first, then left child node, then right child node. NLR. It's given as a NLR. Okay. In the pre-order traversal, the root node is processed first, followed by the left subtree and then right subtree. Okay. Now let us take an example. See here, this is the given binary tree. Okay, binary tree traversal algorithm we are discussing now. In that there are 2 approaches: depth first approach and breadth first approach. Okay, depth first traversal, then breadth first traversal. In depth first traversal, there are three categories available. That is a pre-order traversal, in-order traversal, and post-order traversal. Okay, in that first we are discussing pre-order traversal. So pre-order traversal means first root node will be processed. So here, what is the root node? A. Then left subtree B. Again, left subtree is a root node. So for B will be processed. Again, B contains some child nodes. Okay, so B's left node will be processed C. Okay, then B's right child will be processed, that is a D. Okay, after processing the entire left subtree, we will go to the right side subtree of A. Okay, that is a E. For E will be processed, and for E left subtree is empty, so nothing to process. Then right subtree of E will be processed, that is a F. So the output is A, B, C, D, then E and F. So this is the pre-order traversal output of the pre-order traversal. Okay, so here it is mentioned as a walking order. So how the traversal will happen? First A, B, C, then D, E and F. So this is pre-order traversal. The algorithm we will discuss later. Okay, first we will see how the all the three traversals will work. Okay, so then we will come to the algorithm. Now the in-order traversal. Okay, in in-order traversal, see here it is given as a LNR. First visit the left subtree, then root node, then right subtree. Okay, this is what in-order traversal. It processes the left subtree first, then root node, then finally the right subtree. Okay, now let us take the example. See here, given tree. So as I already told you, first left subtree will be processed. So if you are taking A, for A left subtree is B. And again B contains subtrees. So B is left subtree, that is C. So C will be processed first. See here in output C. Then root node, that is B. Okay, B will be processed. Then right subtree D. Okay, now the entire left subtree is completed. So root node must be processed. So A. Okay, A we are processing. And then right subtree. For right subtree, again E is a root node. So for before processing E, it should go to left subtree. Okay, there is no left subtree, so it is a empty. Then root node E and finally F. Okay, so this is what in-order traversal output. Okay, pre-order traversal output, in-order traversal output we discussed it. So in in-order, how it will be processed? Left subtree, root, right subtree. Again, entire left subtree is over. So root, right subtree. So this is the output for the in-order traversal. Okay, so in exams there is a chance that they will give one tree, and for the tree they will ask you to write the in-order traversal output or pre-order traversal output or post-order traversal output. Okay, so such kind of questions may be asked in exams. Okay, next is a post-order traversal. So in post-order traversal, how the processing will happen means first left subtree will be processed, then right subtree will be processed, and finally root will be processed. Okay, so this is what left, right and root node. So here it is given as a LRN, left subtree, right subtree and then node, root node. Okay, now let us see the illustration. Okay, so here the same binary tree is given. So left subtree means for A, left subtree is B. Again B contains subtrees. So B is left subtree C. Okay, then B is right subtree D, and finally root node B. So left subtree is over. Now before processing root node A, we need to process the right subtree also. Right subtree is E. For E, there is no left subtree, so directly we are processing right subtree F. Okay, and then processing E. Okay, then finally we are processing A. So the output is C, D, B, F, E, A. So this is the output for post-order traversal. Okay, so we discussed about pre-order traversal, in-order traversal, and post-order traversal. Okay, so this is what three depth first traversal algorithms: pre-order traversal, in-order traversal, and post-order traversal. We already discussed about this pre, in, and post. Okay, anybody able to recall it where we discussed it?
Notations.
Notations. So what are the different notations available?
Prefix,
Expression,
postfix, infix.
prefix, and correct. Okay, so that is what the application of this binary tree. So the same way how we created this binary tree, we can create an expression tree. So expression tree we will see as an application in our further classes. So once, if any mathematical expression is given, okay, if you converted that mathematical expression into a binary tree means, okay, if you are traversing the tree using pre-order traversal, you will get prefix expression. If you are traversing the tree using in-order traversal, you will get infix expression. Okay, suppose if you are performing the traversal using postfix, you will get postfix expression. Okay, so expression trees, that is one of the application of a binary trees. So that we will discuss in our later classes. So this is depth first traversal. Okay, if you are looking at, we are processing the child and then means we are going depth wise. Leftmost child we are visiting, then its root node we are visiting, then we are coming to the root node. Okay, so this is depth first traversal. Okay, we are going to the depth of the binary tree first. Okay, so this is depth first traversal. The next is a breadth first traversal. So breadth first traversal means we will perform the traversal horizontally. Okay, first root node, then all its child nodes. Okay, suppose if the root node is having a 2 child nodes, then the 2 child nodes will be processed first. After that, their child nodes, okay, subtrees, it will be processed. So horizontally we will process it. See here in this way. Suppose A is there, means A's subtrees B and E. First A will be processed, then B and E will be processed, then C, D, F, all these 3 will be processed. Okay, so this is the working order: A, B, E, and C, D, F. Breadth first processing, breadth first traversal. Okay, so here this depth first traversal, we will use stack as a data structure. Okay, and for the breadth first traversal, we will use queue as a data structure. Using stack and queue only, we will implement the algorithm. Okay, we will not directly use the stack in the depth first traversal. We are going to use the recursive functions because it is very simple to implement these depth first traversal algorithms using the recursion. Okay, as we already discussed, recursion is very simple to implement, but little bit difficult to understand. Okay, the statements will be, number of statements will be 1 or 2 statements only. Okay, how it will work, to understand that we need some practice. Okay, but coding wise, it is very simple to code. Okay, the depth first traversal we are going to implement using recursion concept. Okay, and recursion, it uses stack by default. Okay, the function calls will be stored in stack. Okay, and the breadth first traversal, we are going to use queue concept, queue data structure. Queue data structure we are going to use. Okay, first let us see the algorithm. Okay, so pre-order traversal means, see here, if root is not null, then process the root. Root is processed first, pre-order, then pre-order of left subtree, process the left subtree, then pre-order of process the right subtree. Okay, that's it. Pre-order algorithm is over. Okay, if you are converting this algorithm into a binary tree, then it will be it will print all the nodes in the pre-order format. Okay, so this is the algorithm. How this algorithm works, okay, so that we will see in our next session. Okay, using a stack, we will create a stack and we will put the function calls in the stack and check how it is working. Okay, so that we will see in our next session. Okay, so any doubt in this today's session?